Waves are not just a feature of the ocean. Waves are everywhere around us, from the ripples in a pond to the light that fills our world. Today, we will delve into the captivating phenomenon of wave interference. Before we explore interference, let's understand what waves are. Waves are a way that energy travels through space. They carry energy without carrying matter. Whether it is the familiar sight of ocean waves, the less visible sound waves that reach our ears, or the light or visible light, which is electromagnetic radiation that can be perceived by the human eye. Waves are essential part of the natural world. The key to understanding wave interference lies in the superposition principle. So, what is superposition principle? The superposition principle is a fundamental concept in a wave theory, stating that when two or more traveling waves encounter each other while moving through a medium, the resultant wave is found adding together the displacements of the individual waves point by point. This principle allows us for the analysis of wave interactions, where waves passing through the same region of space at the same time do not destroy or alter each other. Instead, the displacements of the individual waves in the region of overlap are algebraically summed to determine the overall displacement of the resultant wave. To cut it short, this principle states that when two or more waves meet at a point in space, their displacements add together rather than destroying or altering each other. The principle is observed in various wave phenomena, such as the overlapping ripples in the water created by two pebbles thrown. So, I've got this cool video to help you understand what happens when you throw pebbles into water, and there's a soda can chilling on the water surface. First off, we throw a single pebble, and it creates these ripples in the water. The height of those ripples or amplitudes goes up to about 4 centimeters. Nice and simple, right? Now, let's switch things up. Imagine we throw another pebble on the opposite side of the can. Boom! More ripples, and this time the amplitudes go up to 8 centimeters. Now, here is where it gets interesting. What if we throw pebbles at the same time on both sides of the can? Enter the superposition principle. This principle basically says that when waves meet at a point, instead of canceling each other out, their effects add up. So, we have the ripples from the first pebble, and we've got the ripples from the second pebble. Add them together, and guess what? The amplitudes now total 12 centimeters. It's like a magic. That's the superposition principle in action. When waves collide, they don't cancel each other. They team up and create even bigger waves. Cool, right? So next time you are at the pond skipping stones, just remember the awesome science behind it. Moving on, when we talk about the superposition of waves, we are essentially examining how waves combine when they overlap. This phenomenon is classified in two categories based on the phase difference between the waves involved. These two categories are constructive interference and destructive interference. So now, just take a look for you to vividly understand. Waves can overlap. When that happens, the high and the lows can build upon each other, or they can align in such a way that they can balance each other out when they build upon each other. This is called constructive interference. When they balance each other out. This is called destructive interference. So, let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This constructive interference. Now, here is a moment where all the highs are perfectly overlapping. All the low we see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change the two a video and you'd see otherwise in the next moment. You've got a case where the two lows are now overlapping and this results in a combined low that's much lower once again. We have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. So, check this out. A wave can bounce off of a rigid structure. Let's add a second wave cool. Let's add a second wall and try to confine a single wave. What we have got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument such as a guitar or a float is engineered just right to accommodate standing waves vibrating within instrument, producing beautiful sounds that's good energy. Now, let's give an example of the two categories or types of interference or superposition of waves, which are constructive interference and destructive interference. Let's start with constructive interference. So, just take a look. And as you can see in the illustration, in figure 13.32, in A, you have a stretched string and you send two positive pulses like waves along the string in opposite direction. While in B, when these pulses meet and overlap, it is called constructive interference. What happened is that the combined wave becomes the sum of the two individual waves. It is like adding them together. So, in C, think about the crest of these waves, the highest points. When the crest of both pulses line up or align, the height of the combined wave or the amplitude is the sum of the heights of the individual waves. In D and E, after they overlap and interfere, when the pulses move away from each other and no longer overlap, the waves haven't been permanently changed by this interference. They go back to their original forms. So now let's explain the illustration of destructive interference, which is in figure 13 to 13.33. So, as you can see, have a long stretchy rope and you send two waves or pulses along it. One going to the right and the other to the left. Now, when these waves meet and overlap, something interesting happens. So, in B, when the waves overlap, we add their heights at each point. It's like stacking them on top of each other. This combination is called wave function, which is just the result of adding up the heights of the two waves. So each wave has high points or crests and low points, troughs. Now, when the crests of one wave meet the troughs of the other, they line up perfectly. When this happens, something cool occurs. At the point C, where the crest and the troughs line up, they can cancel each other out. It's like if you had a positive number and a negative number that are the same size. When you add them, you get zero. In our case, when crest and troughs align, the amplitudes or heights of the waves subtract from each other, and you end up with smaller or even zero amplitude. So, in D and E, once the waves pass each other and no longer overlap, they go back to being their normal selves. It is like they were momentarily affected by each other's presence. But it doesn't stick. They return to their original shape and keep moving. So, destructive interference is like two waves meeting, temporarily affecting each other by canceling out some of their heights and then going back to their usual business once they've passed each other. In both illustrations, It is evident that when the two poses move apart, their forms remain unchanged, as though they had never encountered each other or underwent interference. From the repose in a pan to the beauty of interference patterns in light, waves shape the world around us. Understanding wave interference allows us to appreciate complexity and beauty of the interactions happening at every moment. So, thanks for joining us on this journey through the fascinating world of wave interference. Stay curious and keep exploring the wonders of the natural world.